Good morning. This video will focus on the development of a firmware for the CDK board using a PsyCompiler to acquire an analog signal using the ADC that is present inside the digitizer and display the waveform on your computer using the Resource Explorer. This is our setup. We have a Caen digital emulator DT4800 that generates an exponential signal like this one. The analog output is connected to both the CDK board and an oscilloscope. The CDK board, or DT1260, has inside two ADC at 12 bits, 60 megasamples per second. Okay, in order to develop our firmware, we need to start PsyCompiler and create a new project. The new project should be target for this CDK board, and we will call it INSK007 DAQ. In order to acquire the analog signal, we need to place from the toolbar an analog input block. We select the ADC A because we are just parsing a single input, and we connect this block to the oscilloscope. The oscilloscope is a memory mapped block that can be read out using the USB bus. So under the DAQ we can pick oscilloscope. This is the configuration windows for the oscilloscope. An oscilloscope, you can have more than one oscilloscope in the design, but they must have a unique name. Then we can select how many input we have, so one input, and every analog input is associated 4 digital tracks. Now we have no digital tracks, so we can just disable the digital tracks to save time during the compilation. We can connect together the two blocks, and we have to map the oscilloscope on the USB bus, assigning an address. So we click on memory mapping and then auto-assign. The oscilloscope is mapped at address 0 and has 7 control registers. Moreover, it has a memory area starting from address 0 of 64 kilobyte. That is this memory area where there are the waveforms. This information will be useful in the next tutorials, where we will see how to develop to read out memory mapped blocks. Now we start the compiling process. PsyCompiler invoke Vivado to generate the firmware. Starting the compiling process will require about 5 minutes to be completed, and so we have to wait. As soon as the compilation process is completed, Vivado print in green the successful compilation string. At this point, we can load the firmware on the device. To do this, we need to start the board in a bootloader mode. So just disconnect the board, move the switch, and reconnect on the right and reconnect the board. The LED stay fixed on. At this point, we can generate the flash file and start the firmware download on the board. Okay, firmware is loaded, we can press boot application, the blue LED starts to blink. At this point we can open the Resource Explorer, select the CDK, it is automatically detected, press connect, okay, and now we have the oscilloscope and the register for the analog offset regulation. We can choose oscilloscope, press view, and this is the oscilloscope monitor embedded in the Resource Explorer. We can check the channel 1, and now we can set up the trigger and the other parameters in order to correctly view our waveforms. First of all, I suggest you to run in free run in order to find the trigger value. In free run, we can see that the baseline is around 2020, 2200. Okay, so we can set 2200 and select to trigger on channel 1. So we stop and we select to trigger on channel 1, and we set the pre-trigger to the 4%. It is enough. Okay, we are triggering on the noise, so we have to go something higher, 2030, 2300. Okay, now we are correctly trigger, but this signal is saturated, so we have to reduce a little the amplitude. Sorry, that's the frequency, this is the amplitude. Okay, and now we can see also that the 1000 samples that we choose for the waveform is not enough to see the full signal, so we can change it, for example, at 30 nanoseconds per division or more, 50 nanoseconds per division. Okay, so now we have the full view of the waveform. If we have a just positive signal like this, we can regulate the offset register and set it to a different values in order to move the signal. For example, we can set it at 1000, and the signal goes down. Remember, 0 means that we are subtracting about 2 volts the signal. 2048 is the default value, so we are in middle scale. If it's higher than 2048, so for example 2100, we are going over, and if we set it to 0, for example, we are saturating down, so the oscilloscope is no more responsive. So 1000, for example, we move it we move it to a negative part of the ADC scale. So in this way we can center the dynamic of the signal correctly. That's all for this tutorial. Thank you for your attention.